Hi, I'm Julian Williams, and today we'll be talking about the optical properties of ice. And this is courtesy of the University of Texas at San Antonio, as well as the Center for Advanced Measurements in Extreme Environments, or NASA-CAMI. And this is part of the Professional Development Workshop on Extreme Environments for summer 2021. And we'll see a very gorgeous display of ice under polarizing light conditions. So this is where art and science collides. It's a very gorgeous mosaic of colors, and we'll see that right now. So the first concept to understand is the polarization of light. And what that means is described on the left-hand side first. So for an intensity of light that is unpolarized, we have an intensity of I. And as that light passes through a first filter, the intensity is reduced by a half. However, the second filter that is perpendicular to that first filter, by the time the light has passed through the second filter, the intensity is next to zero. However, for the same unpolarized light in a condition where we have two polarizing filters that are instead parallel to each other, the intensity remains the same. And this is displayed again on the right-hand side in the panel where we're seeing the demonstration of that with the light table and the polarizing filters. So here, the intensity is roughly the same. However, when we rotate it at an angle, we see less light being emitted from the filters. And when they are perpendicular to each other, all of the light has been blocked out. So this is the concept behind the polarization of light. So in terms of the optical properties of ice, ice is actually considered a mineral, and it exhibits similar properties as other minerals under polarized light. Thin sections, which is what we normally call these sections of ice, minerals, so on, are usually around 30 microns in thickness. So it stands to reason that we will get a better result in terms of the pleochroism of ice at thinner thicknesses. So here, for this experiment as described in the lab, we have different ice thicknesses in 3 different Petri dishes. And below that, we can see what that looks like under the polarized light. So here we see the sections going from a thicker section to a very thin section. And here we see in the thick section that there's far less pleochroism or play of colors being exhibited. And where we see the very minor areas where there's some colorful display being showed is where we have a little bit of water inclusion or some thinner ice, where we still have some of the pleochroism being able to be displayed. However, as we decrease the ice thickness, we see smaller blades of thinner ice that displays even more pleochroism. And as we get to the very thin ice, we can see a very gorgeous mosaic of colors passing through the polarizing filters. So this is very important in terms of being able to look at ice in different types of imaging systems, not only from optical images, but also from something that we call synthetic aperture radar images, which describe ice or show ice in different ways depending on the type of ice in the image scene. So pleochroism, as we described before with the different play of colors, is much more dominant in the thinner ice sections as we rotate the polarizing screens. And why is that really? So if we think about Snell's law, which describes the refraction of light with respect to a medium, if we think about the thicker ice section, as opposed to the thinner ice section, we've changed the type of medium or the thickness of the medium that the ice that is refracting the light that is incident between them. So this means that the optical properties displayed in thicker ice will be different from the optical properties displayed in thinner ice, since the properties of the medium itself has changed. This is a very intuitive display of the physics behind ice and how it changes over time, and how it shows up in different imaging systems. So this is a very quick tutorial on how to do that, and it's very effective with a minimum amount of equipment. So to speak a little bit more on the physics of polarized light, just before we get into the next section of our exercise, we can talk a little bit about birefringence, which is essentially a double refraction mechanism. And this is displayed in anisotropic minerals such as ice, as opposed to minerals like halite, which are isotropic. And in the bottom left corner, we see here a little schematic of how that works, where we have an incident light source that is split into two different planes. And there we have two rays that are traveling at two different speeds. So where we describe the different thickness of the thin section, depending on the thickness of the thin section, you'll be able to see different first order colors in the mineral through the polarized light. And now we'll talk some more about birefringence and looking at the play of colors and the refracted light through ice crystals from in the field data that has been collected from ice cores. So now I'll turn over to Dr. Ackley. Thank you.